let's put aside these uncomputable functions and leave it to philosophers. We are now going to concentrate only on computable functions. And it appears that these computable functions are not all the same. Some of them are easier to compute and some are harder to compute. And the reasons of this difference are not exactly clear. Honestly, it is not clear at all. Imagine two very similar problems. Each of them takes some graph as its input. So we have some vertices, some edges, a graph. And the question for the first problem is if there is an Euler's path in this graph. And the question for the second problem, if there is a Hamilton path in this graph. The Euler's path is a path which visits every edge exactly once. And the Hamilton's path is a path which visits each vertex exactly once. And the first problem is known to be easy. We have an effective algorithm for solving it. And the second problem is believed to be hard. We don't know an effective algorithm for solving it, and there are reasons to believe that this effective algorithm does not even exist. Now I again use some unclear term, an effective or good algorithm, assuming that if there are effective or good algorithms, there also exist ineffective or bad algorithms. Here I allude to some hidden parameter which allows me to estimate algorithms and to say that some of them are good, some of them are better, and some are worse. And there are actually plenty of such possible parameters, and here I use time, or number of steps of deterministic Turing machine needed to perform the computation. So here for these two problems, which are quite similar, we have a very different results. For one problem we have algorithm which requires not much time, and for the second problem we don't. Let's consider another example. For example, we have two integers, two maybe natural numbers, a, which has n digits, and b, which also has n digits. And now we are going to add these numbers a and b using the column addition method we learned at school. And this method will require at most 2n of elementary additions. And elementary addition is just addition of one digit to another digit. So we see that the complexity, the number of steps we need to perform to accomplish the result, depends on this n, the number of digits. And we can say that the complexity of the problem is O big of n. So it's linear regarding the number of digits in the numbers we have to add. Now imagine that we have to multiply these numbers. So instead of summing them, we have to multiply them. This will require approximately n squared of elementary or table multiplications, which means that the complexity of the multiplication problem is O big of n squared. And we can see now that if when this number n grows, the complexity of multiplication grows faster than the complexity of addition. Anyway, we don't consider multiplication problem to be very hard. Actually, any finite power here tells us that the problem is not so bad. All the problems for which we have a polynomial complexity algorithm, we consider to be tractable. And all such problems form the infinite class called P. So it is all problems for which we know or for which can exist an algorithm with polynomial complexity, defined like this. Aside of this class of tractable problems, which we call P, there is another interesting class of problems which is called NP. Here P stands for polynomial and NP for non-deterministic polynomial. And the problems from the class NP are those problems or those functions for which we can easily or polynomially check an answer. And the ability to check the answer is important. Imagine one day one of your friends comes to you and says that he or she developed a computer program, a chess player computer program, which cannot lose. Now, can you easily check this statement? I believe that no, you cannot, because actually you will have to play all possible chess games with this program to understand if it can lose or it cannot. Now imagine another situation that this friend came to you and tells you that he or she found a Hamilton path on some graph. Now, can you check this statement? Yes, you can. You can just follow this path provided to you by this friend and see if it visits every edge exactly once. So the complexity of this check will be O big of n, where n is the number of vertices in this graph. So this statement is easily checkable, and the finding of Hamilton path in some graph is thus an NP problem, because maybe it's hard to find this path, but if somebody finds it, it is easy to check if it is correct. Now it's obvious that P belongs to NP, because for any problem from P, we can easily check the answer just by solving this problem with polynomial algorithm. But the stronger assertion, if P is less than P, is one of the most famous, most important unproven theorems in modern complexity theory. And because this theorem is not proven, we still have to consider these two options on the slide here. If P is not equal to NP here, and if P equals to NP. So you see class P here, class NP, and nowadays it is believed that there are problems which belong to NP, but do not belong to P, though we cannot prove it. And one of such important problems is factoring problem. Imagine that you have found two different big prime numbers, P and Q, each like 10,000 digits. And you multiply them and you get the product. Both these tasks, like finding big primes and multiplicating them, is feasible for modern computers. And then you give me this number n, and you ask me if I can find these original factors. And we both know that there is only one set of such factors, so theoretically I can do this. But in practice I cannot, because for all algorithms to solve this task we know by now, they all will require too many steps. And with the reasonable assumptions about the growth of our computing power, I will not finish the execution of these algorithms until my death or even until the solar system death. As I said, they require too many steps. So this problem of factoring is theoretically solvable, it is computable, but it is untractable because in practice we cannot solve these problems. And to finish here on a brighter note, in 1994, American mathematician Peter Shor designed a quantum algorithm which solves this factoring problem in polynomial time. So now quantum computers can solve problems that are intractable for classical computers. All of them? Well, probably not. Here on these diagrams you see another interesting class which is called NP-hard. These are the problems for which any problem from NP are polynomially reducible, which means that if we have some magic black box which solves some problem from here, solves it effectively, with this magic box we can polynomially solve any problem from here, from the class NP. And in 1972, American-Canadian mathematician Stephen Cook proved that the intersection of this class of NP-hard problems with the class NP is not empty. And now this intersection is called NP-complete, or the class of NP-complete problems, or NPC, which are the most difficult problems in the class NP. So if we find an effective solution from here, for some problem from here, we can effectively solve any problem from the class NP with this solution. Unfortunately, for factoring problem, it is not yet proved that it belongs to NP-complete problems. And actually, it is believed that it does not. So it's somewhere here. But for all these problems, for NP-complete problems in general, we have a better solution, general solution for quantum computers than we have for classical ones. And for these problems from here, we still cannot say anything reassuring yet, which means that maybe you will be the first mathematician who will develop some quantum algorithm which effectively solves some problem from here, some NP-hard problem.